So, welcome to this fourth lecture on hardware security. So, today we shall be discussing about certain topics on finite fields and also trying to understand about how you can develop hardware architectures for some important finite field circuits. So, today we will be covering these concepts. So, we will be starting with a brief introduction into finite fields or what are called as Galois fields, and then in particular we will be talking about characteristic to finite field operations which are well suited for arithmetic and hardware circuits. In particular we will be focusing on an important design on multipliers which are called as Architectures-1 multipliers, and discuss also about how to perform a modular operation in GF2 which is a very common operations when we are dealing with such kind of finite field primitives. So, to start with a brief introduction into what are called as finite fields. So, a finite field is essentially a field which has got finite set of numbers, and the number of elements in the set is often called as the order of the field, and there is a result which says that a field with order m exists if and only if m is a prime power, that means m is of the form of p power of n for some integer n with p which is a prime integer. This p is often also called as the characteristic of the finite field. Another way of defining a characteristic of the finite field is if we take a non-zero element in the finite field, and the characteristic of the field is the minimum number of times when we add the result to itself. That means we do a plus a so on till k times, and k is the minimum such integer value for which the result becomes equal to 0. So, we have got different characteristic fields. For example, we have got prime fields and we have got binary fields, in which case p the value of p is 2. So, if you are interested for more introduction or more discussions on finite fields, so you can click into this YouTube clip where you can get slightly more details about what fields in general or finite fields imply. So, in particular, as I said, Galois fields are the elements of fields, and elements of the are where the elements of the finite fields can be represented by the numbers or elements from 0 to p minus 1, that means 0, 1 till so on till p minus 1. However, if p is not prime, then the multiplications are not defined. So, therefore, it is important that p in general has to be prime. There is a concept of extension field where you take GFP and you extend it to what are called as extension fields, and often denoted as GFP power of n with n which is greater than 1, and it is the representation is slightly more complex, and the elements in this particular field are often represented as polynomials over GFP. So, I will be detailing this in my talk. So, Galois fields form a very important class of fields which are used in several cryptographic operations. So, it is important to have an understanding about how Galois fields look like and how they can be represented, and in particular how we can do operations on such kind of field elements. So, as I said that the characteristic can be prime and also it can be 2, in which case the field is often called as a binary finite field. So, a binary finite field or a finite field with characteristic 2 is where the set S consists of polynomials with coefficients in 0 and 1. So, here the field is often represented as GF2 power of m. As I said that the general extension form field is GFP power of m. In this case p is equal to 2. So, therefore, this is called this representation becomes GF2 power of m. So, 2 power of m is the order of the field, that means it is the number of elements which are in the field. So, this forms a very important class of important class of finite fields because of the simple reason that the elements or the underlying elements can be represented by values 0 and 1. And this essentially makes it very conducive for arithmetic circuits, because as we know that in arithmetic we are often convenient. We have convenient structures when we have got binary representations. So, in particular when you are talking about GF2 power of m, as I will mention that you can actually represent them by a register of dimension m, where each element in the register is either a 0 or 1. So, in this case the representation or the hardware essentially which is required to represent this element is very optimal. I mean, there is no wastage. On the other hand, you can actually compare it, for example, with GF3 power of m, which is another finite field. If you take GF3 power of m, then the underlying elements will be in GF3. So that means they can be either 0, 1 or 2. Now if I want to represent elements say 0, 1 and 2, then I need 2 bits. So in 2 bits I can actually, or I should be able to represent 4 elements, out of which I am using only 3 values like 0, 1 and 2. So therefore the representation is not very optimal. On the other hand, right, when you talk about GF2 power of m, the representation is optimal, and therefore the hardware, right, which you get is often much more compact compared to the other fields. In particular, as we will be seeing in the next classes, is that the famous advanced encryption standard is constructed using binary finite fields. So it is important to have an understanding about how binary finite field arithmetic looks like. So as I said, that it is important to understand how do you represent elements in a field or in a finite field. So the customary way of doing that is by using this concept of polynomials. So what we do is that we take polynomials over a field f, and this is often represented as an expression of the form of bn minus 1 x to the power of n minus 1 plus bn minus 2 x to the power of n minus 2 plus so on till b0. So in this case, x is called the indeterminate of the polynomial, and the elements bn minus 1 till b0, these belong to the field. So in that case, we say that this polynomial bx is defined over a field f. Now what is the degree of this polynomial? Now degree of this polynomial, right, is equal to L if the value of bj becomes 0 for all j which are greater than L. That means that L is the smallest number with this property. So the set of polynomials over a field is denoted often by this symbol fx, and the set of polynomials over a field which is a degree which is less than L is denoted often as fx with the suffix of L. So therefore, right, when we talk about binary finite fields, then it would imply that the polynomial that I get here bx will have its coefficients which are either 0 or 1. That means the coefficients belong to the field GF2, which has got only 2 elements, either 0 or 1. So now we would like to define operations on these polynomials or operations on these finite field elements. So the most fundamental operation, as we know, right, in fields is addition. So we would like to take two elements ax and bx, which are represented as polynomials, which are field elements, and we would like to define an addition on them. So the usual way of doing that is we try to do it coefficient by coefficient. So we have got two polynomials like ax and bx, which has got coefficients starting from a0 to an minus 1. So what we do is that we basically start adding them coefficient by coefficient. So therefore, right, the addition is very easy to understand, is that it is closed. That means if I take two polynomials and if I add them, then it also belongs to an element in the field. So in that sense, the addition is closed. And 0 would stand with will essentially, the 0 in this field, right, is a polynomial where all the coefficients are 0. So therefore, if I, for example, consider a binary finite field, and if I like just take ax and if I add ax with ax, then I would get that all the elements will have coefficient 0. So therefore, that is essentially the identity element in the field. So the inverse of an element can be found by replacing each coefficient of the polynomial by its inverse in f. That means, like for example, if I take a polynomial ax, then the inverse of ax will be bx, where each of these coefficients are replaced by its inverse. For example, if I take the GF2 power of n field, for example, then and consider a polynomial ax where the coefficients are either 0 or 1. So as we know, in Galois 2, right, or GF2, each element is self inverse. So therefore, right, if I take a polynomial ax and if I add it with ax, then I would get the 0 polynomial. That means all the coefficients would be 0 in that case. So likewise, right, when we as we did addition, so here is an example of how we can do add. For example, the field is in this case GF2, and if I take two polynomials which are represented by these numbers 5, 7 and 8, 3. So in binary, right, this 5, 7 is a hexadecimal representation. So we take 5 and represent it as 0, 1, 0, and 7 as 0, 1, 1, and likewise we take 8, 3, 3. So 8 will stand as 1, 0, 0, and 3 will be 0, 0, 1, 1. So therefore, now in the polynomial notation, therefore I will be starting with 1 here. So this is 1. So this is x. So the coefficient of x is 1. Likewise, the coefficient of x square is 1, but x3, right, the coefficient is 0. So, I do not have that in the polynomial, but I have got x4. So, I have got x4 and then I have got x power of 6. So, this essentially stands for the polynomial or the number 5 7. Likewise, we have got 8 3 and 8 3 has got 1 plus x power of 7. So, therefore, the polynomial is x power of 7 plus x plus 1. Now, if I want to add these two elements, then what I will do is that I will add them coefficient by coefficient. So, therefore, in this case I see that 1 and will be added with 1. So, 1 will be XORed with 1. So, remember that or note that the addition in GF2 is nothing but a Boolean XOR. So, therefore, for example, if I want to add a finite field element 1 with 1, then I basically do an XOR or exclusive OR between 1 and 1. Okay. So, likewise, right, if I take x, then the coefficients are 1 and 1 on both sides. So, I do an XOR with 1 and 1. Okay. So, if I take for example the other coefficients, I essentially do not need to do any operation because there are no overlaps. So, now we can do an XOR between 1 and 1. So, I get 0. So, therefore, this term vanishes. Likewise, 1 and 1 0. So, therefore, the coefficient x also is not there in the final polynomial, and therefore, the final polynomial is nothing but x squared plus x power of 4 plus x power of 6 plus x power of 7. So, one can note that the addition can be implemented with a bitwise XOR instruction, and there are no complicated operations which you need to do, like for example carry, which you often encounter in other cases. So, this is completely a carryless addition. So, but however, right, multiplication is slightly more complex. So, of course, multiplication has got the properties of associativity and commutativity and also distributivity with respect to addition of polynomials. So, this derives from its fundamental field properties. So, therefore, if I take two polynomials ax and bx and want to multiply them, then one can observe that if I take for example a field gf2 power of n, that field is for a finite field. So, when I multiply ax with bx, there is a chance that the coefficients will become more than what the field allows. So, therefore, what we need to do is we need to do a modular operation, so that the final result is brought back to the field. So, therefore, right, we often have got, once we have defined these two operations like both the addition as well as the multiplication, then we have got this as what is called as a commutative ring. And in particular, right, where each element or each non-zero element in this field has got its own multiplicative inverse, right. That means if I have or if I can define an element which if I multiply with that element gives me the identity element in with respect to multiplication, then I call that as a field. So, therefore, this structure becomes a field. Now, a ring will become a field for certain choices of this polynomial which I do with which I do this modular operation. Okay. And with that restriction or with that restriction of the polynomial, the structure qualifies as a finite field or becomes a finite field. So, therefore, right, I mean the qualifier or the property which the polynomial needs to satisfy is often called as the irreducibility property of the polynomial. So, this you can imagine as an analogy to what are called as prime numbers when we deal with numbers. So, an irreducible polynomial or a polynomial dx is irreducible over the field say GFP or Galois field P if and only if there exists no two polynomials ax and bx with coefficients in GFP such that the product of ax and bx is equal to dx. That means, dx factorizes or factors into ax and bx, where ax and bx are of degrees greater than 0. That means, I do not get any non-trivial factors of dx. So, therefore, right, if your field is GFP, then with suitable choices for this reduction polynomial, that means, if this reduction polynomial satisfies this property of irreducibility, then I get a field. So, therefore, if you for example take that this particular polynomial essentially satisfies the properties and of irreducibility, then finally I get a finite field which has got p to the power of n elements. So, p is the characteristic of the field and n is an integer which is defined by the degree of my irreducible polynomial. For example, like if the degree of my irreducible polynomial is say m, that means I have got a polynomial of the form of x to the power of m plus so on. That means, any element which is there in the field will have a degree which is lesser than m. So, therefore, the number of elements that I will find in that field is p to the power of m, okay, and this is often customarily represented as GFP power of m or GFP power of n if m be n, and then GFP power of n is called as the extension field of GFP. So now here are some possible examples, but we essentially can have bigger tables. For example, with degree 1, this is an irreducible polynomial. Degree 2, we have an irreducible polynomial. Degree 3, this is an irreducible polynomial. Degree 4, this is another irreducible polynomial. So these are all irreducible polynomials to define fields like gf2 power of 2, gf2 power of 3, gf2 power of 4, and so on. One can observe that these are all either trinomials or pentanomials, but you cannot have an irreducible polynomial with even number of terms. One of the reasons is if you do that, in this case, for example, like if you have like x power of 4 plus 1 as an alternative choice of an irreducible polynomial, then you can trivially see that x plus 1 is a factor of that polynomial, and therefore that doesn't qualify as an irreducible polynomial. So therefore, write x power of 4 plus x plus 1 or x power of 4 plus x cube plus 1 on the other hand does not have such trivial factors, and therefore that qualifies as an irreducible polynomial. So what I can now do is that I can take arbitrary polynomials. I can take arbitrary polynomials where the coefficients are in GF2, and once I take such polynomials and I start reducing them, or I do modulo operation with any of these like polynomials, like say GF like x power of 4 plus x plus 1, then I can construct the field GF2 to the power of 4. That means what I will try to do is I will take any polynomial which has got 0, 1 coefficients, and then I will divide that polynomial with x power of 4 plus x plus 1 as a choice of my irreducible polynomial, take the remainder becomes an element in my field. So if I start constructing such fields, then the maximum number of elements that I can have in the field is 2 to the power of 4. So I can have like 16 possible elements in the field, but at the same time, right, this essentially is just one possible I would say like one possible annotation of the field. If you take another polynomial, then you will have another annotation of the field, okay, and one can show that all these fields, right, are equinumerous, but they are not equal. They are essentially what are called as they are equivalent in some sense, because they are isomorphic to each other. So with this background, right, I mean, I just give you I will not go or solve this particular problem, but rather I will just ask you with this question. That means how you can construct a GF2 power of field using the polynomials x to the power of 4 plus x plus 1 is something which I leave to you at this point as an exercise. So now let us give an example of how we can do a multiplication. As we have seen addition, for example, which was very easy, but multiplication would be slightly more complex. For example, if I take elements like 5, 7 and 8, 3, which are elements in GF2 power of 8. So 5, 7 is as represented here and 8, 3 is as represented here. And if I take the polynomial notations, then I have got the first element as I said before, and likewise is my second element. Now when I am multiplying these two elements, then I can observe that for example, I have got a degree here x power of 6 and I have got a degree here x power of 7. So when I multiply them, then I have got my degree which becomes x power of 13. Okay. Now x power of 13, right, is not there in the field, because my field which has got GF2 power of 8 in this case can have maximum degree of 7. Okay. So it cannot have x power of 8 or more than that as its degree. So what I need to do is, therefore I take the final result. So for example, this is the product of my two polynomials or the two elements, and then I need to reduce it, or I need to take a modulo operation with this polynomial. That means with the corresponding irreducible polynomial for GF2 power of 8. So in this case, I have taken the irreducible polynomial as suggested in standard tables, which is x to the power of 8 plus x to the power of 4 plus x to the power of 3 plus x plus 1. So therefore if I take this polynomial and if I reduce it, then or take the modulo with this polynomial, then I get x to the power of 7 plus x to the power of 6 plus 1. So note that this polynomial is in GF2 power of 8 because the maximum degree of this polynomial is 7, and therefore this is a field element. I get an element in the field. So likewise, right, I can show that multiplication is also closed, okay, and therefore I essentially have got a nice field structure on which I can define my arithmetic, both addition as well as product. So therefore, right, the finite field is therefore, like here is another example of how we can do it, or how we can do it. So this example is with slightly smaller field. For example, the field is GF2 power of 4. So there are two elements like x power of 3 plus x squared plus 1. There is another element x squared plus x plus 1. When I am doing multiplication, the first step is a normal school book operation where I elaborate or get the partial products, and then I start adding them. Note that the addition is done in GF2. That means if you have got two x square elements like x square and x square, then you don't get that reflected in the result, because when I am adding x square with x squared, that means that the coefficients are XORed. That means 1 gets XORed with 1, so you get 0 here. So therefore, in this case the result is x to the power of 5 plus x plus 1. Again, like before, this is not a field element because this does not belong to GF2 power of 4. So therefore, I need to again do a modulo reduction operation. So the modulo the irreducible polynomial for GF2 power of 4 is say x to the power of 4 plus x plus 1. So basically what I do is I take this polynomial, divide it by x to the power of 4 plus x plus 1, and I take the remainder. The remainder in this case is x squared plus 1. So there are different choices of multiplication algorithms. Okay, so for example, I have listed few of the important ones like Karatsuba, Mastrovito, Sunarcock, Massey-Omura, Montgomery, and so on. You can observe that most of these algorithms have got a space complexity which is quadratic with the bit length of the arguments. On the other hand, Karatsuba seems to be interesting because it has got which is something lesser than that. So it is O(n) to the power of log 3 base 2. That means it is more efficient compared to the other ones in terms of their space complexity. However, the choice of the multiplier is often defined by or determined by applications. For example, like if you have got characteristic P fields, that means GFP fields, then often Montgomery multiplication is a better choice. On the other hand, right, if you design properly, then the Karatsuba multiplier has got its own merits, and therefore, right, it is an important and interesting class of algorithm to study. So there are several other operations also, right, which you will probably see when you are dealing with finite fields. So the other important operation which we also encounter along with multiplication is squaring. So in particular, when we are doing squaring in GF2 arithmetic, then the computations are very efficient. So this slide shows how one can do squaring. So for example, the input polynomial which is ax is represented in this register, and I said that for example this is an element in GF2 power of n, where n is some integer value, and then when you are trying to do a squaring operation, then what you just need to do is you need to interpose the corresponding bits by zeros. So this you can understand easily by if you just consider this calculation. For example, if you take a polynomial say ax which is essentially nothing but an minus 1 x to the power of n minus 1 plus so on till a0, and then you want to do a squaring. So basically what I mean is I need to do ax and I would like to square that. So the square of this is nothing but ax to the n minus 1 x to the power of n minus 1 plus so on till a0, and you would like to square. So now I just leave it to you with this result here, but without going into details, is that when you do a squaring in normal operations, right, you get often coefficients which are multiples of 2. But in this case, since you are dealing with this field that is GF2 power of n, then all those elements will go to 0, because in this case 2 is nothing but which is congruent to 0. So therefore what you will get is basically an minus 1 square, but again an minus 1 is an element in GF2, so n minus 1 square is also an minus 1, and n minus 1 x to the power of 2 times n minus 1 plus say n minus 2 x to the power of 2 n minus 1, which is like the next element. So you will get this as say rather n minus 2 into 2 plus so on till a0, which is the constant term of the polynomial. So therefore, right, you can imagine that if you try to note the result, right, the result essentially is nothing but copying the original elements like a0 and a1, and the final one is an minus 1, but the coefficient here is x to the power of 2n minus 1, and this is the coefficient of this is x power of 0, the coefficient of this is x squared. So these are all even degree terms, whereas the in between ones are nothing but 0. So this is your n minus 2. Okay. So therefore, right, what you basically get is nothing but this you take the original coefficients, but you just interpose them with zeros, and that is nothing but your ax square. Of course, as you can see that x to the power of 2n minus 1 is more than 2 to the power of n. So therefore, this number is not an element in the field. So you need to do a reduction operation and bring the result back to the field. So so with this background, right, I mean we can go back and Okay, so yeah, so therefore, what you still need to do is you need to bring the result back to the field, and the final result essentially should be back to the field, means you need to do a modulo operation so that the result becomes back or comes back to GF2 power of n. So, so the other important operation, as I said, is the finite field multiplication. So, in finite field multiplication, right, there are different forms of multipliers, but in particular, in specific, right, I will be trying to explain the Karatsuba multiplication, which is a very common form of combinatorial multiplication. That means the result, when you are giving the inputs ax and bx and the corresponding irreducible polynomial, it gives you the result ax into bx mod px in just one single clock cycle. Okay. And there are different forms of combinatorial or combinational Karatsuba implementations. Two very common forms of algorithms are what are called as the simple Karatsuba multiplier and the general Karatsuba multiplier. So, in particular, right, let us see how the simple Karatsuba multiplier works. So, in simple Karatsuba multiplier, you basically take the input ax and bx which you would like to multiply, and you split each of the polynomials into two parts like ah and al, and likewise bx into bh and bl. So, now when you want to do this operation, that is ax into bx, in a normal school book multiplication, right, what do? We basically have got 4 sub multipliers. You have got to multiply al with bl, h with bl, and likewise h with bh and al with bh. Okay. Now, in the Karatsuba setting, what you do is you basically do the multiplications or sub multiplications h and bh and al and bl. Okay. But the other part, that is h into bl plus al into bh, you write them in this form. So, you basically elaborate this term and write it as h plus al into bh plus bl. Note that if you do this, then there are some extra terms which are getting incorporated, which are h into which is h into bl plus al into bh. You would like to subtract that, okay, and in JF2 arithmetic, subtraction is nothing but addition, because both of them are XORs. So, therefore, in order to eliminate them or cancel out them, you basically add h into bh plus al into bl, and therefore, this is equivalent to h into bl plus al into bh. If you do that, right, then one can observe that the sub multiplications that we need to do are al into bl, h into bh, which we are again reusing here, and the third multiplication, which is like h plus al into bh plus bl. Of course, you need to do some extra additions, but you have reduced 4 multiplications to 3 multiplications, okay, and that gives you saving. So, you can apply this in a recursive manner. So, you can take m, and assuming that m is a power of 2, you can decompose into m by 2 blocks, which you can again sub decompose, and you can carry on applying this simple Karatsuba multiplication in a recursive manner. Okay. But at the same time, it is important to understand that this Karatsuba multiplier becomes efficient if you do a proper thresholding. For example, right, if you go down to bits, right, then what you are basically saving is AND gates, because in terms of with respect to bits, right, a multiplication is nothing but an AND operation, and the addition is nothing but essentially an OR operation or an XOR operation. Okay. So, therefore, right, when you are what you are basically saving is multiplications. That means, if you just go down to 1 or single bits, then you are saving AND gates, but you are expending other gates. Okay. So, therefore, that may not be very like efficient. So, basically, you have to stop this applying the simple Karatsuba technique at a suitable point, so that you essentially can leverage the saving, like the saving which you are getting at the cost of something. So, therefore, right, thresholding is a very key step when if you want performance when you are implementing Karatsuba multiplications. So, there is another flavor of Karatsuba multiplication which are called as general Karatsuba multiplication. In general Karatsuba multiplication, instead of splitting into 2, we split into more than 2. Okay. For example, an m bit multiplier is split into m different multiplications, and that essentially leads to another flavor of multiplication which are called as general Karatsuba. So, I will come into that in slightly more details, but before I go into that, let us remember the LUT structure which our FPGA has. Okay. So, which I showed or discussed in the last class. So, now if I take these 2 multiplications which we discussed, like the simple Karatsuba which I elaborated and a general which I just mentioned, right, as another topology of the Karatsuba multiplication, and if you observe the lookup table and the gates, right, then you see an important observation. For example, right, if you see when we are increasing the finite or the m or value of m or the size of your finite field, then in the context of general Karatsuba, then we see that the gate count increases significantly compared to the simple Karatsuba. Okay, that means that general Karatsuba consumes more amount of resources. But if you go down with smaller field sizes, like for example field sizes of 4, then you see that the gate count, right, of the general Karatsuba is essentially 37. But interestingly, if you see the lookup table counts, then you see that the lookup table count is less compared to that of the simple Karatsuba. For example, here you see it is 11, whereas here it is 16. Okay. So this is because the general Karatsuba for smaller dimensions or in general has got a better LUT underutilization. For example, the LUT underutilization for the general Karatsuba is something like 45% when you are having a field value of 4, whereas the underutilization for simple Karatsuba is always around 65% or 66%. So therefore, right, you can actually adopt a strategy where you can actually apply the simple Karatsuba when you have got a higher dimension of m, but as you go down when you are doing this recursive operation, you switch from the simple Karatsuba to the general Karatsuba, because for smaller field sizes the general Karatsuba would require lesser number of LUTs and therefore would be more efficient. So this particular structure is something which we call as a hybrid Karatsuba, and therefore, right, it can give you to more compact designs. So basically what we do is for all recursions which are less than say some specific threshold. So in this case, in our case it was 29, but it will vary from platform to platform. So one can use the general Karatsuba multiplication or the school book or even the school book multiplier, but for all higher recursions, right, we use the simple Karatsuba as essentially as our broad Karatsuba operation. So for example, like in this case we give an example with 233 bit. 233 is because, you know, like many of our cryptographic operations works on 233 bits, as I will be telling in the next classes. So 233 bit is something which is not an even number, so we cannot decompose into equal partitions. So what we do is we decompose into say one partition of 116 bits, another partition of 107 bits, 17 bits, and then carry on this decomposition. And as I said that there is a specific threshold below which I switch my algorithm. So I essentially apply a different flavor of multiplication. In this case I have applied general Karatsuba, but even a school book multiplication would be interesting to see. The main thing is that you have to change from the standard Karatsuba, because otherwise, right, there will be wastage of the lookup tables. So what we will do is we will basically we'll stop here, and in the next class, right, we will try to go into more details where we will be trying to go into or we will try to understand how to implement this basic structure. So we will try to see how we can realize this structure on Verilog, and we will see that how we can develop a design or rather develop and complete end-to-end Karatsuba multiplication algorithm on hardware. So with this I would like to thank you.